test coming up in Math 1 on Monday that's going to be an important one. So I'm going to make a key here. Some of these problems I've worked through before and some of them I haven't, but I'll kind of talk my way through maybe not all of the problems, but some of the problems. Multiple choice tends to be pretty tough. If you look for some key things, oftentimes you can do some elimination. This particular pretest doesn't always write things in the same order that we're used to in this class. So we need to look at it pretty critically. So before I even look at what the sequence is, it's saying recursive function. Now I can eliminate B and C because neither is written in a recursive form, which would start with something like f of x or f of n equals f of n minus 1 or something like that. Has got to be in that for that recursive form. So that gets us down to these two guys. Now they both start at the first term equaling 6, which is what we show here. So that's not a difference. The function notation itself looks fine in both cases. It's the what's going on that we need to define which one is correct. So if I add 12 to 6, I get 18, but if I add 12 again, I don't get 54. So it can't be this one. Process of elimination tells me it has to be this one, but it is because if I'm multiplying by 3, that will work for the sequence. So I call that the what's going on. All right. Explicit functions do not have the f of n minus 1. They'll start with f of n, but then we'll have the what's going on or something along those lines. Now this particular sequence, well, hang on, let me back up a second. So it can't be C and it can't be D because those are in recursive forms where they have the f of n minus 1 written into them, which is the previous term. So looking at my numbers here, going from 60 to 30 to 15 to 7.5, that's going to be timesing by a half or dividing by 2, but this is really how we want to see that. In A, I don't have anything about timesing by a half, so that can't be it. In B, I have the half, but I've got this sort of weird n minus 1, but by process of elimination, I've decided that this has to be the answer. And if I plug in 1, I get 60 times 1/2 to the 0 power, and anything to the 0 power is 1, so this is just 60 times 1, which does equal 60, so that checks out with that first term there. So if I plug in 1, I should get 60. Which recursive function describes the sequence here? Again, I'm looking for recursive. It looks like A has a recursive aspect to it. B is okay. C does not have recursive in it. D does. So I can eliminate C. There's no f of n minus 1 in there. I'd have to see that for the recursive. So going from 2 to -3 to -8 to -13 looks like I'm subtracting 5 each time. And so it looks like A has the -5 for the what's going on. I subtract 5 from the previous term to get to the next term. But my starting point here isn't written correctly. This should say f of 0 or f of 1 equals 2, and it says f of n equals 2. So it can't be this one, but it's pretty close. Here they give the starting point as f of 0 equals 7. Well, I don't even have a 7 in my table here. So it can't be B. And f of 1 equals 2, that works here. My first term is 2. And I'm taking away 5 from the previous term. It's got to be D. Which recursive function describes the arithmetic sequence? Arithmetic indicating that it's adding or subtracting to get to the next number. So if I take this and I turn it into some sort of a table value, I can say n and f of n. When I have 3, I get 10. That's what this is saying. And for the fourth term, I get 16. It's arithmetic, so that tells me it's not multiplying to get from number to number, it's adding. So the next one would be f of 5 equals 22. I'm adding 6 each time. So plus 6 is my what's going on. And I'm looking for recursive, so it's got to have the f of n minus 1. So A has f of n minus 1. But the starting point isn't right. F of 1 equals 10? No, that's not true because f of 3 equals 10. So it can't be A. And we don't, in this particular problem set, they're not always writing everything in the same consistent pattern. They're mixing it up, which makes it a little tough for us sometimes. Looking at B, I have recursive. I'm adding 6, and I start at f of 3 equals 10. That matches here. I'm adding 6 to the previous term. That matches there. To get to the next term, we have B. Which recursive function best matches the explicit function? Explicit, this is the one where I want you guys to be able to write it. The recursive is great and all, but that's the one we want. So they're giving the explicit, and they're giving it in an order we're not used to. If I rewrote this, it would be more like what we've seen in class. That would be the way I would rewrite that. But the number that's multiplying the n is the what's going on. So I'm taking away 3 to the previous number each time. So here I'm taking away 3 from the previous number. It could be C. B is also taking away 3 from the previous number. A is adding 6. That can't be. D is adding 6. That can't be. So it's between these two, and the only thing I have to do now is figure out which of these starting points, f of 1 is 6 or f of 0 is 6, is correct. So what I'm going to do is I'm going to try the 1 first. Is negative 3 times 1 plus 6 equal to 6? So I'm plugging in the 1, and I'm checking to see if I get 6. Well, negative 3 times 1 is negative 3 plus 6, and that definitely does not equal 6. That would be 3. So that's not true. It can't be C. It's got to be B. Circle all the explicit functions that correctly match the recursive function. Well, I'm multiplying by 11 over and over again. So the what's going on has got to have something like 11 to the nth power if I'm multiplying over and over again. So that's a power. This is geometric. I'm starting at 0.1 equals 1. Looking at C, it looks like I'm kind of in the right place, but this f of 1 doesn't make sense in this case. So it can't be C. That's not how we've seen explicit functions. F of 0 equals 0. This is a recursive function. That's not what it's asking for. These are both recursive. So it's got to be between A and B. If I take 1 and I raise it to any exponent, if I take 1 and I raise it to, say, the second power, that equals 1. If I take 1 and I raise it to the third power, that equals 1. So this is just 11. It doesn't matter what n is. This is all just going to turn into 1s times 11. So it can't be that one. It's got to be A. There's our 11 to the n minus 1. We haven't really talked about this as a type of adjustment, but that's really what it is. But I don't know that that's necessary to understand that's the right answer. Okay. Circle all the explicit functions that correctly match the recursive function. So here's what I'm going to do on this one. I'm adding 6. So that's my what's going on. So that's got to be 6. How many times am I adding it? As many times as I want, 6n. And when I plug in 1, I have to get 15. If I look at A, here's the 6, but it's not going to multiply times the n like we need it to in an explicit function. So it can't be A. B, 6 times n, I'm looking for that, that looks good, plus 9. So what I want to do is I want to double check this one. If I put in 1, do I get 15? So when n is 1, 6 times 1 plus 9, does that equal 15? And in fact it does. Now this says circle all, so that means we really need to check all the others. That's definitely the right answer. C, if I distribute the 6, if I multiply the 6 times both of these terms, I'm going to have 6n. So let's try this one. If I put in 1, do I get 15? So is 15 plus 6 times 1 minus 1, is that equal to 15? Well, this becomes 6 times 0, which is 0, plus 15, and that does equal 15. So this is also an answer. And here I don't have the 6 times n, I've got 15n. If I put in 1, I'm not going to get 15 here. So I know that D is not right. Alright, number 8. Circle all the explicit functions that correctly match the recursive function. Again, when it says circle all, you better check them all because you might miss some. Alright, on the recursive function, this is saying that it starts, the pattern starts at when x is 0 or when n is 0, I get an answer of 3, and I'm doing what to that? I'm adding 2 each time. So if I made a table of values here, you can always do this, I haven't done it for all of them, but if I said if n is 0, f of n is 3, if n is 1, then I have to add 2 to the 3 to make that 5. If f is 2, I need to add 2 to the 5 to make it 7, and so forth. That's what this pattern is saying. Take the previous number, add 2, you get the next number. Now, what's going on is I'm adding 2 over and over again, so that's going to be 2n in an explicit function. So it looks like A would work. If I put in 0, do I get 3? Is 2 times 0 equal to 3? Oops, hang on, I missed a part there. Is 2 times 0 plus 3 equal to 3? So I'm plugging in 0 here, and I'm setting it equal to 3, and yeah, that's true. So that's an answer. Here I've got 2 times n again, though it's in the parentheses, it's still going to turn into 2n. So what if I put the 0 there? Is 2 times 0 minus 1 plus 5 equal to 3? Well, 2 times 0 minus 1 is 2 times negative 1 plus 5. Does that equal 3? Yes. Negative 2 plus 5 equals 3, so that's an answer. And I need to keep checking. If I plug in 0 here, because I've got the 2 times n, and I'm running out of room here, I'll bring it around over here, is 5 plus 2 times 0 minus 1 equal to 3. And in fact, this and this are the same. They've just rearranged. They put the 5 out in front. So yeah, this is going to become 5 plus 2 times 0 minus 1 is negative 1. 5 minus 2 equals 3, and so that one checks out. And the only thing different between D and A is they've just simply written the order backwards. But if I take 3 plus 2, that's the same as 2 plus 3 in basic math, so this also has to work. 3 plus 2 times 0 equals 3? You bet it does. Okay. Which sequence best matches the explicit? So here we have an explicit function. Again, this is a little different than we've written it in class. We have this n minus 1. It's an exponent, so we need to be careful. So here's what I'm going to do with this. We can plug in whatever we want to get our answers. So I'm going to pick some easy numbers. We did this one in class, actually. I'm going to pick some values. I think we did this one in class. Maybe not. So if I put in 0 here, ooh, that's going to be a problem. We haven't learned how to do that in this case. So let's skip the 0. That might cause some problems. How about 1? We'll keep these exponents positive. So if I go 2 times negative 3 to the 1 minus 1, that gives me 2 times negative 3 to the 0 power, and any number to the 0 power here is 1. So that's 2 times 1 is 2. So when n is 1, x is 2. If I plug in 2 times negative 3 to the 2 minus 1, that's going to be 2 times negative 3 to the first power, which is just negative 3. That's going to be negative 6. Now what I'm doing here is I'm multiplying by a negative 3. So 6 times negative 3 would be negative 18, and I can take that pattern as far as I want to go. Negative 18 times a negative 3 is negative 54. The what's going on is what's being multiplied over and over again. That's what the exponent does. So I look at my values here, and I need to match them here. It looks to me like A looks good, but everything here is negative, where I'm going opposite. Oops, wait a minute. Negative 6 times negative 3 should be a positive 18, my mistake. And then the 54 should be negative. Right, am I right on that? I'm questioning myself because usually when we have an even number here, oh, I know why. No, that's right, because it changes to odd with the minus 1. So the sequence I'm looking for there is B. Which sequence best matches the explicit function? Here again, I'm going to just plug in some values. I'm actually going to do this one in my head. Use this as an example. So if I plug in 0, negative 2 to the 0 power is 1, times negative 5 would be negative 5. Only one of these sequences starts with a negative 5. It's got to be D. Determine if the following sequence is arithmetic or geometric. So here we're looking at what's going on. If I'm changing from 4 to 8 to 16 to 32 to 64, that's geometric because we're multiplying. The recursive formula, we're going to say the what's going on. It's called the common ratio, but I like to call it the what's going on. It's just times 2 to get to the next number. We sort of have a choice to make here, because it doesn't define if this is the first term, the 0th term, the 9th term. It doesn't say. So I'm just going to go 1, 2, 3, 4, 5. I'm going to count those as 1 through 5. So the recursive formula, I need this starting point, is going to be f of n, the next number in the sequence, equals the previous number in the sequence. We write that as n minus 1, f of n minus 1, the function. Now, what do I do to the previous number to get to the next number? I times by 2. Now, this is sort of how a computer works, and this is what I've told the students. This is not the way humans generally do math, but if you're going to be computer programming, you've got to kind of understand this. Now, I have to tell the computer where to start the pattern. So I say f of 1, when n is 1, I get an answer of 4. That starts the pattern, and then we double and double and double and double as far as we want to go. The explicit formula starts out the same, but after I write my function notation f of n, this is just the answer, the output for any given input. Now I start with my 2, my what's going on. Now I'm multiplying over and over again. We can do that as many times as we want, but multiplying repeatedly involves exponents. So 2 to the x power. Now the trick to this is I've got to make an adjustment. So I'm going to plug in the 1 for the x. Actually, sorry, that shouldn't really be x. I get hung up on x's. This should be n for this problem, but it doesn't really matter. I'm going to plug in 1 for n. I should get 4 for an answer, but I don't think I will. Does 2 to the first power equal 4? No, that equals 2. So what can I do to make that change? Well, I can't add or subtract, not and have it work for the rest of the pattern, so I've got to multiply. So 2 to the first power is 2 times what number would give me 4? You can solve the equation, or you can, if you can do it in your head, you can plug in a 2 there. And this now is true, so now I can go times 2, and this should work for any term. So let's put the fourth term in, for example, just to test it. Is 2 to the fourth power times 2 equal to 32? Well, let's see, 2 to the fourth, 1 2 is 2, 2 2s is 4, 3 2s is 8, 4 2s is 16, and if I multiply by another 2, that is going to be 32. It checks out. All right. Determine if the following sequence is arithmetic or geometric, then state the recursive and the explicit formulas. I want to look at the pattern here and see if I can see what the pattern is. It appears to be adding by 7 each time. Every time we take a step in the pattern, I add 7. That would be arithmetic. That's your adding or subtracting. Geometric is when you multiply to get to the next term. So the recursive formula, we've got everything we need. This is our what's going on, and we need our starting point. So we say f of x equals f of x minus 1. What this is saying is the next term in the sequence can be found by taking the previous term in the sequence and adding 7 to it. And I want to say where that pattern starts. So I'm going to say the function of 0, when I plug in 0 for n, I get 5. That's saying where the pattern starts. And then I add 7 each time after that. The explicit, f of x, they're using n's and I'm switching to x's. Oh well, I can live with it if you can. I need people in the background. This is kind of boring. I hope this isn't too boring for anybody watching it. So I take the what's going on. What am I doing to get to the next term? That's 7. I'm adding it over and over again. That's actually multiplying is an efficient way mathematically to add over and over again. How many times am I adding 7? As many as I want. But now if I go 7 times 0, if I plug in the value for the first point, I have to get 5. But clearly this isn't 5. So how would I have to adjust that? When it's arithmetic, I'm using adding or subtracting, so I can adjust with an addition of 5. And now I should be able to plug in any number I want to get any value in the sequence. So if I want to plug in 100 there, I can, and it should work just fine. All right, 13. They're giving us some values here. What they want us to do is simply plug it into here. Now this is a main idea in mathematics. The way they write it is this is the n value. So I'm going to say 2 times 4 plus 7. So I'm taking this part of the value and I'm plugging in the 4. That's going to be 8 plus 7 is 15. And so when n is 4, the answer is 15. Now, I'm going to do the same thing with the 7. 2 times 7 plus 7 is going to be 14 plus 7 equals 21. Now, this is a sequence. What's going on is a little tough here because we're jumping numbers. So plugging in again the 22. 2 times 22 is 44. Plus 7 equals 51. So when n is 22, the answer is 51. And I'm going to keep going. 2 times 40, I'm plugging in 40 for the n, plus 7, that's going to be 80, plus 7 is 87. showing the work up here, I'm giving the answers here. This one's going to be a little trickier. We've got some exponents to deal with. Calculator's just fine. So I'm plugging in 2 for the n value. So this is going to be 6 times 2 times 2 minus 1. Well, 6 times 2 minus 1 is 1. So 2 to the first power is really just 6 times 2, which is 12. If I put in 3, 6 times 2 to the 3 minus 1 is going to be 6 times 2 to the second power. 2 squared, 2 times 2 is 4. So 6 times 4 is 24. And notice that my sequence here isn't jumping around. Now it's going to 4 and 5. And if I can see what's going on here, it appears as though I'm doubling. Let's double check that here. I'm going to put the 4 in for the n this time. So 6 times 2 to the third power. 2 to the third power is going to be 4 times 2, so that's 8. 6 times 8 is 48, and I can see very clearly that I'm doubling to get to the next term. Give the first 4 terms of the sequence of the recursive formula. F of 1 is 42, and I'm adding 6 to get to the next term. So they're telling me what I start with here. Now, I'm adding 6 each time, so 42 plus 6 is going to be 48. 48 plus 6, the previous term, plus 6 is going to give me the next term. Let's see, that's going to be 54. But I can also take that pattern backwards. What would have had to been here to add 6 to it to get to 42? Well, that would be 36. Okay, so I'm taking 6 away to go backwards, adding 6 to go forward in the pattern. All right, give the first 4 terms of the sequence with the recursive formula, starting with f of 0 equals 36. Well, I'm actually going to add that over here. There's nothing wrong with adding that. So when x is 0, or when n is 0, I get 36. Now, to get 1, I've got to put that 1 in right here. No, what am I saying? That's not right. That's not right. Sorry about that. I get to doing this and I start making mistakes myself. What this recursive formula is saying is I take the previous term and I multiply it times a third. Well, 36 times 1/3 becomes 36 divided by 3, which is 12. Now I take the 12 and I multiply it times a third. It's going to be 12 times 1 is 12, divided by 3 is 4. And I'm going to continue dividing by 3. 4 times 1/3. 4 times 1 is 4, divided by 3. Now I'm going to suggest we leave that as an improper fraction, 4/3. And now if I take the 4/3 and I multiply that times 1/3, 4 times 1 is 4, 3 times 3 is 9, and so forth. Tricky. It's tricky. Alright, so I hope this is working for us. Let's take a quick peek at the last page. Geometric sequences. We have a couple geometric and a couple arithmetic. I'm actually going to start with the arithmetic, so I'm going to do 19 and 20 first and then go back to 17 and 18. So for the arithmetic sequence, what I've said is I've given sort of a formula. I've said take the largest, or the term farthest right in the sequence, or farthest along in the sequence, and subtract it from the term to the left, the farthest, or the least in the sequence. So if this was 1, 2, 3, 4, 5, and 6th term, then I'm going to take that -7 and I'm going to subtract 18. Now, so the difference between these, and then I divide it by the number of spaces between them, plus 1. So that's going to be 4 plus 1. And that's going to give me the common difference. So that's going to be 25 negative divided by 5 gives me a negative 5. And now all I have to do is take away 5 each time to get these answers. So 18 minus 5, 13. 13 minus 5 is 8. 8 minus 5 is 3. 3 minus 5 would be negative 2, and negative 2 minus 5 is negative 7. This is the equation to solve for the common difference. Right there, that'll work right there, just fine. Okay. The next one, I've got 2 spaces to fill, so if I call this the first term, the second term, the third term, the fourth term, I'm going to take the fourth term and subtract the first term. So 27.5 minus 5 divided by number of spaces between them plus 1. Can't miss that plus 1. So 27.5 minus 5 would be 22.5 divided by 3. I believe that is 7.5. So that's our common difference. So that means I've got to add 7.5 to each term. So 5 plus 7.5 would be 12.5. Plus another 7.5 is going to give me 20. And plus another 7.5 is 27.5. So that checks out. All right. So most of my students seem to do pretty well on this. This is fairly new. Let's look at the geometric. The geometric's a little different. Here I'm not adding or subtracting to get to the next term. I've got term 1, 2, 3, 4, and 5. I've got to multiply a number. So how I've shown this is I've got to take 3 and multiply it times some number that I don't know. Let's call that x. And then I've got to take that number and multiply it to get to the next step. So it's going to multiply by another x. So 3x squared. And then I multiply that by another x. And then I keep doing that until I get to my 5th position here in this one, where I say 3x to the 4th equals 243. And that's my equation. So the first thing I'm going to do here is I'm going to divide both sides by 3 to get that x to the 4th by itself. I'm going to use some space over here. I happen to know what that is divided by 3. That's 81. At this point, I ask students to try to think about what they think that number would be in their head. So what number times itself 4 times is going to give you 81? A key here is, since 81 is odd, x has to be odd as well. So that kind of narrows it. It takes 50% of the numbers down anyway. But here's how we need to solve this. I take the square root, but it's not really the square root, it's the 4th root of both terms. Now, to do that, I've shown the students how to do that in at least the graphing calculators. If they have their own, that's great. Now, what happens here is that the 4th root and the 4th power here cancel. So we end up with x equals, and now I take that 4th root of 81. So in this problem, I'm going to go, or in this calculator, I'm going to go to math. I'm going to pick this any power key. I'm going to put the 4 in and the 81. And I'm going to make a guess. Hopefully my guess is correct. I guessed 3, and it is. So the common ratio, that's the word for multiplication, is 3. So I'm multiplying by 3 each time. So 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81, and 81 times 3 is 43. So these are really the numbers that we want in there. All right, last one. 6, first term, second term, third term, fourth term, fifth term, sixth term, seventh term. So I'm going to say 6x squared, 6x to the 3rd power, 6x to the 4th power, I don't know what that is, I keep going, 6x to the 5th power, and I get 6x to the 6th power, it's pretty ugly there, for 6 million. So I'm going to say 6x to the 6th power equals 6 million. Now to solve this, I'm going to divide both sides by 6 and get the x to the 6th by itself. Now, I like to write it out this way, but really what's happening is it's the number of spaces plus 1 is your exponent. If you notice that, that's great. So then that's going to be x to the 6th equals 1 million. And to cancel that exponent, I'm going to take the 6th root of both sides of this equation. So this will cancel this. And so I get x equals, now I'm going to go to the calculator. I think I know the answer, but I'm not sure. If I take the 6th root of 1 million, I think it's 10. Oh yeah, it is. Okay. So that means I'm multiplying by 10, so 6 times 10 is 60, times another 10 is 600, times another 10 is 6,000, times another 10 is 60,000. So each time I'm adding a 0, times another 10 is 600,000. And the magic number that I want to win on the lottery, 6 million. So what's the common ratio? Times 10. All right, test on Monday. It's a biggie. Do well. I hope this helps. If you actually spent the time and went through this with me, yeah, like I said, I hope that really helps you for the test. I will see you on test day.